How is that different from evaporation? What temperature does evaporation take place at?
The same.
Just,
sorry, not the same. Sorry, that's different.
Just, it takes place at whatever temperature you happen to be at. Yeah? It just happens at any temperature.
But it's like faster and slower.
Exactly. So if you get, the closer you get to the boiling point, the faster it's going to evaporate. So that's why a puddle on a hot day will disappear faster than a puddle on a cold day. And we're going to watch a little Tyler video because sometimes people get confused about what happens with boiling. And Tyler really doesn't want you to be confused. So let's just see, is this on? Yes, it is. Okay, good.
Here's one of the biggest things that people don't understand in chemistry. Keep this in mind.
Okay.
When a liquid boils or evaporates to become a gas, the molecules don't come apart. So let's talk a little bit about liquids, evaporation, boiling, and molecules. So here is a very tiny glass of water. Well, it's a tiny glass of water that we've zoomed in zillions and zillions of times so we can see what makes it up. And what we see is that this glass of water is made of all of these water molecules.
Okay, so that little particle that contains one oxygen atom and two hydrogen atoms is called a water molecule. Okay, and it looks a bit, if you were to turn it right side up, or upside down, I guess, it would look a little bit like Mickey Mouse. Okay, with the circle and then like the two ears on top.
One oxygen atom connected to two hydrogen atoms. That's why we call it H2O. So our glass here contains lots of molecules of liquid water. Let's now make some steam, some gas water. What we're going to do is we're going to heat up this liquid water. And as we heat it up, the molecules in it are going to start moving faster and faster and faster until some of them are moving so fast that zoom, they can jump, shoom, right out of the liquid water, enter the air above that liquid, and start flying around. Now, these guys up here are molecules of steam, also known as gas water. So here's the main point. When they're liquid water, the molecules, H2O, are packed really close together. When they're gas water, or steam, they're still molecules of water, one oxygen and two hydrogens. It's just that now they're not as densely packed and they're flying around in the air above the liquid. Here is the mistake that so many people make and that I don't want you to make. This, as we said, is the way that water does evaporate. Here's the mistake that people make. Here is another glass of water. So many people think that when water molecules become gas, that they have to break apart, that the atoms that make up those molecules split apart from each other. And that's the only way that the liquid water can become gas or steam. So we have these molecules here, and they have to rip these atoms apart. And so that if we were to zoom in and look at steam, we wouldn't see water molecules, but we'd see all of these pieces of the molecules, all these atoms ripped apart.
Which one of these is correct? The one on the left is correct. Yeah? How do you know? Yes? It keeps the shape. If you have water vapor, it should still be water. If you rip them apart, do you have water anymore? No. If you were to rip them apart, would that be a chemical change or a physical change? That would be a chemical change. When atoms either break apart or come together or rearrange themselves in new molecules, that's when we have a chemical reaction. So when you have a physical reaction, the particles look the same before and after. If you have a chemical change, the particles look different before and after.
This is wrong. Here's the
You guys
big
were
red
correct.
X. I don't want you to make that mistake. On the other hand, here is the right way that boiling or evaporation happens. The molecules look just the same in gas as they do in liquid. They do not, big red X, they do not split apart into the atoms that make them up. Same in liquid, same in gas. Okay, now this isn't just true for water. This is true for anything, for any liquid that can evaporate or boil to become a gas. So here I have a tiny amount of gasoline. The molecules look like this. 8 carbon atoms surrounded by 18 hydrogens. And then here I have some alcohol, a carbon with a bunch of hydrogens, and then an oxygen. Now, alcohol and gasoline can both evaporate. If you're like me, oh, you love the smell of gasoline.
Okay,
No, no.
don't breathe, don't inhale solvents or like hydrocarbons. They are extremely bad for your brain. They are cancer causing. Yeah, it's just not good. Okay. If you're working at a gas station, you'll inhale fumes a little bit because you're just there, you get exposed to it. But that's not the same as like going and smelling it on purpose. It's just like, don't do that, bad idea.
Which is like those vapors that you get when you're filling up your car. Oh, I love it. So you know firsthand that gasoline can evaporate and become a gas. Here's the point though. Here is the wrong way to think about evaporation. If a gasoline molecule looks like this, the wrong way to think about it is that these molecules would come apart into the pieces and into the individual atoms. And the same thing here with the alcohol. This is wrong. These molecules here have split apart into atoms and pieces of molecules. On the other hand, the right way to think about this is that both the alcohol and the gasoline molecules just nicely lift out of the liquid when they turn from liquid to gas.
So the molecules stay intact. They just separate from one another.
This is what the liquid would look like. The molecules are all tightly packed together, and here's what the gas would look like. The same molecules, they're just
floating
around in the air and they're further apart.
Okay, we're going to leave it there.
So once again,
No. Okay. All right. So that's basically what's happening there. And we're just going to go through the rest of page 46 really quickly. A molecule is a type of particle. Particle is a word that we're going to start using a lot for this unit and all the rest of chemistry, quite frankly. Okay, a molecule is a particle. Another type of particle is an atom. Yeah, an atom is another type of particle. A particle is basically just a small bit of matter. We'll get more specific in Unit 3, okay? But molecules are particles and atoms are particles. How many atoms is a water molecule made out of? You can show me your fingers. How many? An oxygen and 2 hydrogens. So it's made out of 3. Molecules are always made of 2 or more atoms stuck together. If you have less than 2, then you've only got 1 and you've just got an atom. You don't have a molecule. Okay, molecules are little groups of atoms. Now, I don't know if you remember this from last year, but there are 2 major categories of elements. Does anybody remember what they are? You may or may not have learned this in grade 8. Yeah? Metals and nonmetals. So, hydrogen and oxygen, are those metals? No, that means they must be nonmetals. So they are nonmetals. So if you ever get asked about the type of element, don't get confused. Usually, if I say type of element, that means either metal or non-metal. And it's interesting because molecules are always made of non-metal elements. Okay, I'm going to give you some examples of molecules. We've got CO2. Is carbon a metal?
No.
No, that's a molecule. How about that? How about that alcohol? C2H5OH. We have carbon and hydrogen and oxygen. Are any of those metals? No. How about NO2? Nitrogen dioxide. Is nitrogen a metal? Nope, we know oxygen isn't. So you can see that all of the molecules are just made of non-metal elements. There are no metals. We'll learn what they do later. No metals allowed. Okay, then we have our little picture. Yes, no. Now, this is a little bit of enriched stuff, but I'm going to let you do it along with me here. The atoms in a molecule are stuck together by these really strong forces called a bond. So if we have our water molecule, there's this stickiness that holds the hydrogen to the oxygen, and that little sticky bit is called a bond. Okay? And bonds are strong. Okay, this part here, this is enriched. Okay, bonds are strong. There we go. And these particular bonds are called covalent bonds. Bonds in a molecule are called covalent bonds. Covalent bonds. Again, this is enriched. You don't want to do the enriched? No problem. Nobody cares. It's all good. Right? I won't get mad at you at all. Okay? Totally your choice. And because they are bonds, they are strong. Yes, covalent bonds, any kind of bond is strong. Do you remember what the word inter means? Inter means between. Okay, so inter is between. There's a reason that I teach you these prefixes in isolation, because you'll see the prefix inter all over the place through science, and it always means between. Okay? So inter means between. If you take an international flight, it takes you between nations. In between the water molecules, we have intermolecular forces. What do you think intermolecular forces are between? They're between molecules. Intermolecular forces are forces. Whoops, I spelled force with a P. What is wrong with me? So if I was to draw a little picture of a water molecule, here's my oxygen, and here's my hydrogen. Okay, I'm going to draw them sideways. And I'm going to draw another one here, an oxygen, and a couple of hydrogens. It turns out that the oxygen is a little bit positive. Okay, so the oxygen, which is the bigger one, is a little bit positive. And no, I'm so wrong. Oh my God. The oxygen is not positive. This is what I get for teaching at the end of the day. The oxygen is negative. Does anybody need whiteout? We're good? Okay. Good. All right. The hydrogens are a little bit positive. Okay, so let's put the positives in the hydrogens. Dear me. What does positive do to negative? They attract. So, in between this positive and this negative, the positive attracts the negative. And same thing here, the positive attracts the negative. Are these two water molecules bonded together? Do they have a bond between them? Are they part of the same molecule? No, I have two separate molecules, but there's still forces between them. What do we call those forces between them? We call them intermolecular forces. And if you don't like the word intermolecular forces, because that just has way too many words in it, way too many letters, you can call those IMFs. Isn't that a nice abbreviation? So much less writing. Okay. And intermolecular forces are not strong. They are weak. So, I've got some magnets here, yeah? And in order to break apart this magnet into smaller pieces, would I be able to do that with my bare hands? No, right? Because it's molded together, it is bonded, all the little bits of this magnet are bonded to each other, okay? But magnets stick to each other. The forces that hold the magnets to each other are like the intermolecular forces, where this is a molecule. Can I break the molecule apart? No, because those bonds are strong. Can I break the intermolecular forces? Yes, because they are weak. So when we boil water, we break the intermolecular forces, because when things are, like, let's say I was moving this really, really fast, like everything's moving super fast, things just break off naturally, right? If stuff starts moving really quickly. So that's why heating things up, you can get separation of molecules from one another. But I mean, I could make this move as fast as I wanted, and I'm not going to be able to break this molecule in half, right? So at the boiling point of water, what is the boiling point of water? Do you guys know? 100 degrees, yes. There is enough energy, so at the boiling point of water, there is enough energy to break the weak what? What do we call them? Intermolecular forces, yes. But if you don't like that whole long word, what can you use? IMFs between the molecules. But there is not enough energy to break the strong bonds. Yeah. And if you want like a little extra, you can go so far as to say covalent bonds. So when water boils or evaporates, the water molecules break apart from each other, but the molecules themselves stay intact and they don't split apart into individual atoms. So again, all of that is like enriched stuff, okay? So if you like it, yay. If you don't like it, that doesn't matter. Here is some condensation. Now condensation, not really too exciting unless we start looking at using condensation as a way of separating things. Imagine that we have some salt water, okay? And the salt water is in a flask. Okay, so this piece of glassware here is called a flask. Here we have salt water, so that is a mixture of salt and water. It is salt, NaCl, plus H2O. It is a mixture. It says NaCl. What is NaCl? That's a really good question. I think you were away for that. NaCl is salt. That is sodium. And that is chloride. And that is salt. Okay, good question. Okay, so we've got salt and we've got water and we have a mixture of those two. Now, do you remember the video we had yesterday where we looked at melting salt? Okay. What temperature did we have to be at to melt salt? It was like 800. Okay, crazy, crazy. And that was just melting it. Did the salt boil? No. Okay. The only reason we got it spattering was because, remember, the CO2, what did it do? It turned directly from solid to gas. What is that process called? Tell your partner. Solid to gas.
I will depositing deposition, and then there's.
So what you're going to do is you're going to imagine yourself at the Subway restaurant. Okay, and you're going to imagine what do you want a little squeeze of on your sandwich, just to make it a little bit tangy. A little lime. Sublime. Okay? Subliming.
Yes.
Okay. All right. Now, so who boils at a lower temperature? Water or salt? Water. Water boils at a lower temperature. It boils at 100, but salt isn't even melted until 800. Crazy, right? So if we start and we put a Bunsen burner underneath this and we heat the whole thing, what's going to happen to the water? The water's going to come out. This is our water here. We get our steam and it goes out. And then we got fancy glassware, okay? We got a tube that's like a tube within a tube. We've got glass on the outside and we've got glass on the inside. And what we do is through the outside part of the tube, we pour cold water and that makes the outside part of the tube cold. And then the cold water comes out the other side. So it's continually getting cold water coming in, new cold water. What happens to steam when it hits something cold? It becomes water again. What's that word for when the steam becomes water?
Condensation.
That is condensation. Okay, so remember on the bathroom mirror when you take a shower, what do you get on the mirror? Condensation. So this is called a condenser tube. All right, and the water's going to come out and it's going to condense, and we're going to end up in here with water, gas is going to turn into water. What state will it be now? Liquid. Okay, so now we have liquid water and it will drip. Okay, and then you can collect the fresh water. What's going to be left behind? Salt. So if you had seawater and you had one of these things, you could actually make yourself some nice drinking water. Okay? Yeah.
But isn't there a bunch of other stuff in seawater?
But most of it also has a higher boiling point than water, so everything else is going to stay behind. Yeah. Yeah. So for the most part, it's pretty good. Plus, by boiling it, if there's any bacteria or anything in there, you're also going to be killing them off, right? So if you have water that you think is not safe because it's got maybe bacteria or amoeba in it, right? You don't want to be drinking any of those things, then you boil it for 10 minutes. And then that will sterilize it. It will kill all bacteria and amoeba and all kinds of things. Okay, so let's look at our little distillation animation. This whole process where you take the water and you boil it out and then you recondense it is called distillation. Let's go look at the little animation here. Yes, that's what distilled water comes from. That's this process.
When performing a distillation, first the condenser is filled with cold running water. Next, heat is applied.
Okay, why does it not go big for me? Let's make this big. Big! There we go. Okay.
When performing a distillation, first the condenser is filled with cold running water. Next, heat is applied to the mixture, which is to be distilled. The mixture is heated until it boils, and the hot vapors will travel up the distillation head. Measuring the temperature of the vapors helps us to identify the liquid being distilled, and will help to confirm its purity. If the vapors are pure, they will have a constant temperature equal to the boiling point of the liquid being distilled. As the vapors travel into the condenser, they will be cooled and will liquefy. The liquid droplets, called the distillate, run down the condenser and are collected in a receiving flask. A liquid can be easily separated from non-volatile contaminants by using a simple distillation apparatus such as this one.
And that's it. Okay, so gas to liquid is called condensation. And we're just going to take a little look at what happens if you have aqueous salt. Remember, what does AQ mean? AQ stands for? Aqua. Yeah. Aqueous. What does aqueous mean? Dissolved in water. So we're going to take a look at what happens when we've got salt water. So we're going to take salt, which is aqueous, and we're going to turn it into salt, which is solid. So that's the other part of the distillation. And there's a little animation here. Hopefully this is good. I don't remember how good it is, but let's take a look and see if it's any good.
So here's the dish of water, and if we look very closely, the water molecules are evaporating, and as they evaporate, the concentration of the sodium and chloride ions increases, and the charges bring them closer together, and the attractions hold them together, and they recrystallize as salt.
Okay, do you recognize that structure? Right? That was the one that we had the other day. So as the water goes away, and it's no longer holding the little ions with their positive and negative charges with the water's positive and negative charges, those positive and negatives click together like little magnets. Positive says, oh, negative, click. And the negative says, oh, positive, click. And they all just click together. And we're going to watch that one more time because it's really short. Okay. Whoops, that's not what I wanted to do. I don't want to go all the way back to the beginning. So I have to click again in here. Okay, there we go.
So
Oh no, that's okay. Okay.
here's the dish of water. And if we look very closely, the water molecules are evaporating. And as they evaporate, the concentration of the sodium and chloride ions increases, and the charges bring them closer together, and the attractions hold them together, and they recrystallize as salt. And that's why.
Okay, and that's that. So that's just kind of to give you a nice little thing there. So salt, remember, is Na. What do you notice about the capitalization here?
Only the first letter is actually.
Only the first letter of every element is capitalized. So when we start using our periodic table, you'll see that if there's only one letter, it's a capital. If there's two letters, only the first one is a capital. Are there any that are three? There used to be, but I think they've gotten rid of them now. So if there happened to be three, only the first one would be capitalized. It lets you know that you've started a new element. So for example, Na is sodium. And Cl is chlorine. Chlorine, although when it's together in a compound, it actually gets called chloride. So I'm going to call it chloride for now. Okay, we'll talk about why that is later. What symbol do we use when it's dissolved in water? AQ. What symbol do we use when we have salt crystals left?
Solid.
S. S for solid. AQ for aqueous. Is good? Okay. Okay. This is just showing the video. We're not going to go through this because we already saw it, but if you ever want to look at it, you can. And now we're going to watch some sublimation, dry ice. So what's happening here is we have our, do you guys know what compound makes up dry ice? Carbon dioxide. Do you guys know the chemical formula for carbon dioxide? Who's carbon? What's the symbol for carbon? C. And then we have oxide. What's the symbol for oxygen? O. How many oxygens do you think if we call it dioxide? 2. So it's CO with a little 2 down at the bottom. Okay, so that is carbon dioxide. And if we have dry ice, that is CO2. What state would that be? S. And you can actually see here, down in this area, what's coming off? Gas. Okay, so that is CO2 gas. And let's watch a little video of some sublimation. So this is actual real dry ice. Dramatic music. I'm not sure this is worth the video, but anyway, this is what sublimation is. And you can see the solid is getting smaller and little gas things are coming off, and there's some dramatic music in the background, and there we are. Okay. Okay, that was it. Woo! All right, I may have to rethink that one. I'm not sure that's worth the watch, but that's okay. And now we've got, this one I think is better. Let's see. This is the sublimation of iodine. So let's check this one out, see if it's any better. So this is solid to liquid, or no. What have I done wrong? I've made a mistake in my book. Take a look at what I've written here.
Sublimation solid to liquid.
That is wrong. Oh no. What should it be? It should be solid to gas. And what else did I do? Deposition. I said it was liquid to solid. It should be gas to solid. So I need to fix this. How have I missed that for so many years? Okay. Let's take a look at the sublimation of iodine. Iodine's fun because it's purple. It's a really deep purple. So here's some elemental iodine. They look like blueberries. Don't eat them. So they're going to heat it.
That clicking sound is so satisfying.
And you get this beautiful purple vapor. Okay, and there's no liquid in between because iodine, along with carbon dioxide, is one of those weird things. Oh, and then here we go. We put ice in a flask on top, and what do you notice is happening at the top? Let's see what happens. We're going to zoom in close. Time lapse. What did we get? You got iodine crystals on the bottom of the flask. Okay, so that
how would we do that?
it deposited.
Is it toxic?
Yes.
Oh.
So no, you wouldn't make jewelry out of it because it would, at room temperature, it will sublime at room temperature, so your jewelry would not last for very long. It would be like, okay, and now it's gone, and I'm now inhaling toxic fumes, and I am dying. So, not a good business proposal. Okay. All right. And that's it for that. Let's see. I don't know that the iodine myth is worth watching, so we're going to skip it for now. And I think you guys could do pages 50. You could do page 51. There you go. Yeah.
So we are going to look at
No, we're
two
not.
different things that we mix together.
No, we're not. There we go. Thank you so much. Thank you. Is this really it? Is there page 52? What's happening?
Yeah, I don't think that's a very good choice. You look good on the lemon. Oh, I watched the lemon.
Pardon me. Yes, we did. I'll grab that for you in just a minute. Folks, we're also going to do pages 56 and 57. If you want to work ahead, you can also do 58 and 59.
Yes. Oh my God, that killed me so hard. I hate that fog so much. You so bad. Body and
Oh, well, you could hand back some tests. Let's see. Vivian's already seen hers. You could, well, Abby's gone to the washroom. You could hand back Mateo's test, and if you wanted to explain to him his progress report. Okay. There you go. And who else? Ryan. Ryan also.
Okay.
Okay. You can hand those back. And I think that's it for now. When you're done with it, just hand it up and because I use them to like kind of bring it up for
Anything else for me to do? Any tests, quizzes from other class?
That needs to be.
What other class?
My other class.
guys, I like the next question. Yo, you can do this. I can't survive for 1 second. 46. Oh, I thought you were like, what? What? No. I'm scared. I don't want to leave. But I don't want to start anything wrong. Why would he, bro? Like daydream. Okay, that's not true. I hate it. Like, close enough. Oh my god, was he no?
And tomorrow we're going to
almost
start looking at
some
some
elements.
elements.
That's why. Yeah. So that was like all like it's not allowed. It's so not allowed. That's so funny. That's not funny. That's why I like he's right. Was he actually a YouTuber for the day? No, never. It didn't happen. We almost did, and that's scary. That's now our first time. Every time he sees me, I was like, that's not are you trying to put your imagination? No, it's definitely 100% true. He's like a British guy. Oh, he's scary. Thank you. Okay, so this is definitely actually going to talk to you. No. Why? I was thinking which one? Yo, I'm not doing it right now. I am too busy drawing my meat. She's drawing. I love it. She's so fun. Are you hungry? Look at that. Hey, I don't need
Thank you. Perfect. And the other thing we're going to do is
I saw my friends, so that was good. Yesterday I went to find. Oh, I didn't really. Actually, it's kind of nice. Come on. You sure? Yeah. I don't like that. Listen to my back. What everyone else is double. My brother's double jointed. It's so scary. He does this weird thing. It's fine. Stop. I can't do it. It's like the thing my brother can do, like legs and stuff, and still together. Sorry. Okay. Let's see. Who can I drag into the back? Yeah. Okay. I think we're gonna have to go like that. Yeah. You should drag Sue in there. I don't think it's like going that way. What? And break. Look at her big, beautiful eyes. Yeah, let's go there. Why are you reading this? Dead. I take it back. I should do yeah, great job. No, not great job. It's really bad. Only 3 days? Yeah, I need to today is eggs. Well, now you gotta do it because it's eggs. What should I do? Yo, I'm thinking of making you do a Harry Potter shirt. Wait, actually, wait. It's like eggs. Let me think of an eggs to Harry Potter. Or at least one of my favorite ships. You could just say this is a friend's favorite. Yeah. You do AUs? Yeah, probably. I mean, as long as the characters are dead. Yeah. You could just like an AU, like, I love Julie. You could do an AU where Lily survives, because that's actually possible.
I'm going to go over a little bit of page 57 with you. So if you're having trouble at all with page 57, I'm going to just do one or two of them with you. Okay? So we'll take a look. Whoops.
Oh, what are you talking about? Okay, I'm gonna flip the canvas to my stuff and then I'll flip you over again.
Thanks.
Okay, friends, if you have not yet gotten to page 57, let's go to page 57 right now so we can do one or two of them together. 57. 57.
It's a circle.
So what this is going to do is it's going to test if you understand what the difference is between a chemical and a physical process based on looking at the particles. Did we end up here? Is there a new substance or is there no new substance?
It's a mixture.
We have nothing new. We started with squares and circles, and what did we finish with? Squares and circles. What did we do with these two things? We just mixed them. So basically, you're going to take a look at this and say, was this a chemical or physical change? That's the first thing. Chemical or physical? This is physical. If it is physical, you're going to decide, did I melt it? Did I freeze it? Did I evaporate it? Did I condense it? Did it sublime? Did it deposit? Or did we mix it? Or did we separate it? What did we do here? Does this look like melting? No. We mixed it. This is mixing. Now, if it happens to be a chemical change, you're lucky. You're just done. You're like, it was chemical. Done. Okay? So let's take a look at maybe this one here, part B. Did we end up with something new? Yes. And if you ended up with something new, then that is a chemical change. And then you don't have to decide. Like, there's no types of chemical changes. It's a chemical change. So you're going to do that for the rest of them on that page as well. You're going to decide, are they chemical or are they physical? And if they're physical, then you have to go through this list here and say, which one of these things happened? And if you finish page 57, you can go on and do page 58. Okay? Yes. Yeah.
To come here with stuff.
Okay. I just feel like I don't have as much for you to do as maybe some other teachers do, but over here. Yeah.
Color action. It's Steve. Steve? No, I don't think it's mint. It's just maybe it's just a really bad mixing. Is this just really bad mixing?
You know what I might do?
Yes.
I could also ask Ms. Lamb if she has extra work. She's got four blocks right now. and that's really busy for her, so I'll ask her.
I
if she
think,
has
wait,
any
I think it's
more.
mixing, but it's like, you put water in oil.
Okay.
Like
Sure.
one floats
Yeah.
out there. I think it's fantastic.
Okay.
Yeah, excellent. Because for me, it's really hard because AP Chem, like, salt.
Okay.
Do you know what I mean? Like it's like this level, right?
Miss,
Yeah.
Cody.
Yes. Hello, Cody.
Other one.
Oh, perfect. Okay. It was 55, I think. Yes. Perfect. Okay, Cody. And then we have today's. And 51. Yeah. Thank you. Perfect. Sorry? Oh, yes. Quiz. Oh, I have not marked the quizzes yet. They probably won't come back until Monday because I'm trying to get my Chem 12 back because they have a test on like Wednesday next week, so they need to study over the weekend. So yeah.
Miss,
Yeah. I do not. Oh, yeah.
Okay, I did my best with this. I just don't like this thing with the actually, yeah. Oh my God, stop switching layers.
So maybe this is like directly. And that doesn't happen very often. Okay, no,
Why? I should probably make Yo, Calista, I think she's.
Okay.
I thought it was
So you're at the restaurant, what restaurant are you at? It's fast food. You're in Subway. Okay, I did not understand what you did. Tangy. So you asked to put a squeeze out. Lime. On it. So sublime. Sublime.
It's a line.
Or you can imagine, you're in a subway tunnel and along comes the train, so there's not a train for one.
Thank you. You look so weird. I know he did.
Oh, time to get our phones. And my clock is slow. Yes. Okay. Okay. The lesson will be recorded and everything will be on Teams. Yep, perfect.